Another application of water pumping is in energy storage. Recall in week 5 that we had discussed other forms of energy storage where pumped hydro was one of it. Here you lift water from a lower level to a higher level and store the energy in the form of a potential energy, the lifted up potential energy of the water. And when you need it, you would like to convert that potential energy into kinetic energy, make these impellers rotate, and then the shaft of the motor which is rotating, the motor will now act like a generator which will transfer the mechanical energy into electrical energy. So in this way we will get out the electrical energy which can be used for powering up the loads. So to do that, we place a pipe in this fashion. This is called a penstock, and at the end of it there is a jet. By controlling this valve, you can control the jet here, which will make the impellers to rotate and thereby get the mechanical power, which will get converted to electrical when this machine now acts like a generator. In this system, the pumped portion and the hydral portion both use the same machine pump configuration. When it is pumping up, this is a motor and this will be a pump, a centrifugal pump, let us say. And when you are generating electrical power output, this will become a turbine and this will become a generator. So here, if you are using a DC motor, then you will get a DC output. Alternately, if you would like to get an AC output at different power levels, so the pumping power could be at one rating, the power at which you will take out the power, retrieve the energy can be at a higher power. So a decoupled system like that will be something like this. So you have the PV panel pumping using the DC motor and a centrifugal pump in this fashion here to pump up the water from a lower level to an overhead tank, a reservoir, what we could say. And then from this overhead tank, I use a penstock and then use it to run another turbine. And the shaft of the turbine is connected to a generator, and the output of the generator is a DC output, or it could be a three-phase AC output depending upon whether you want to have a DC generator or a AC generator. So another advantage with this is that you can pump up the water at a lower power. You can spread it over the whole day. The water can be accumulated over the whole day. So the hydraulic power needed will be low. And then you may need the electrical output during the night time, let us say, for a shorter period. Let us say you pump up in 4 hours and then you would like to utilize this electrical energy which is stored in 1 hour, then this rating can be higher. The power rating of this can be higher, and you could probably have the output in AC. You will pump up using a DC motor and then you will take out the power in the form of an AC using an AC generator and alternator, and this AC can directly be used for powering up many loads. So if you decouple it, you will see that it is much more advantageous, but only thing is that you will have to pay for an extra turbine and generator. So this is also another scenario. We have discussed at length about this part, pumping up water from a lower level to a higher level. We have discussed about how to calculate the hydraulic energy for this part. Let me briefly discuss about this part now for this particular application of pumped hydro. The right side portion, which is shaded, is called a hydel system, and depending upon the power rating, it could be called hydel, a mini hydel, a micro hydel, or a pico hydel. Pico hydel, the ratings are of the order of 5 kilowatts. Micro hydel of the order of 50 kilowatts. So let me discuss a simple pico hydel system for small homes and community usage kind of a thing, and let us just look at briefly the important equations. Consider a reservoir, and from the reservoir a penstock, and at the end of the penstock there is a jet, and the jet of water is impinging on the blades of the impeller, and this acts as the turbine, which converts the kinetic energy of the water at this jet to the mechanical shaft energy. And we know this height here. Now I will give a symbol uppercase h, because lowercase h we have used for total dynamic head in the case of water pumping. So this, for retrieving the energy, I will use this uppercase h. And this point here at the jet, we will say Q dot is the flow rate or the discharge rate. We know the hydraulic energy EH, which is rho Q GH, and we also know the hydraulic power rho Q dot GH. Only difference, note that the height is different. This is the height up to the center of this axis of the jet. Consider this turbine, this Pelton wheel, and where the jet at the end of the penstock is impinging on the Pelton wheel and converting the kinetic energy to mechanical energy. And this is Q dot, the flow rate. The hydraulic power rho Q dot GH, rho is 1000 kg per meter cube as before, 9.81 meter per second square is G, and we have the hydraulic power at this point, and we can take it as approximately 10 Q dot H kilowatts. Flow rate is in meter cube per second, and if you take flow rate in liters per second, then it will become 10 Q dot H watts, where flow rate is in liters per second. So all these remain the same except the value of H. So as an example, 100 meter head, 5 liters per second flow has a hydraulic power of 5000 watts or 5 kilowatts at this point. Now let me define that this is the fluid velocity at this jet, the jet velocity uj. Now the turbine velocity is ut. The angular speed of the turbine omega t. This is the tangential velocity. Now Ft, the force, tangential force on the turbine, is given by 2 rho Q dot uj minus ut. Uj is the jet velocity, ut is the turbine tangential velocity. Uj minus ut having a unit of meter per second. Q dot having the unit of meter cube per second, and rho having unit of kg per meter cube. So you have overall kg meter per second square as the overall unit. So meter per second square having the acceleration units, and you have kg, so mass into acceleration, so this is having the unit of force. So this can be derived. So tangential force is this much. We also know that the hydraulic energy rho Q G H A, I will say HA is the actual measured physical height from the center of the jet to the center of the outlet of the reservoir. So this potential energy is converted to the kinetic energy as half rho q uj square. This is the form half mv square rho q mass uj square jet velocity. Now rho q and rho q I can remove, so you will have 2gha is equal to uj square. So now at this fluid velocity, I know the jet cross section area is aj, let us say. aj into uj will be q dot. So I have these three relationships. From these three relationships, let us say q dot can be expressed in terms of uj. uj itself can be expressed as 2gha. So when you replace q dot and uj here, so you will have ft as a function of only ut. Ut is the only variable, the tangential velocity. Everything else. So you say the power, the mechanical power is efficiency times jet power, which is the hydraulic power here, which is efficiency times ft into ut. ft into ut is the jet power. Now this, because this whole ft itself is a function of ut into ut, so you will have ut square term and a ut term. So I will in general put it as Pm is equal to alpha 1 ut minus beta 1 ut square. So q dot and uj replace it in here, and ft you replace it here, you will get the mechanical power in terms of ut, that is the tangential jet velocity. Now ut itself can be expressed in terms of the angular velocity. So I have the radius r. So ut is equal to omega t into r, which is the radius of your impeller. Now Pm can be expressed as alpha omega t minus beta omega t square. Now this would be the power equation, the mechanical power available at the shaft, where alpha and beta are given this form. This can be, as I said, you substitute, you will get this relationship. Now using that power equation, the mechanical shaft power Pm, which is equal to alpha omega t minus beta omega t square. See that torque and power are related. Torque into omega is power. So therefore torque, the shaft torque can be obtained as power divided by omega t, angular velocity, which is equal to alpha minus beta omega t. So this is a falling, this is linear and a falling slope. Now when t is 0, when the shaft torque is 0, you will see that omega t is alpha by beta. Now that should correspond to, see, if you are using it for generating and it's generating 50 hertz, and 50 hertz is the synchronous frequency. So that should correspond to 2 times the synchronous frequency. I'll tell you why. Therefore you need a gear ratio so that 2 times synchronous frequency and alpha by beta correspond. And at the output after the gearbox, it will be Tt by the gear ratio. Now let us just plot and see what I mean. This line, red line, is the torque line. Consider this, you will see here alpha minus beta omega t. So when omega is equal to omega t is 0, you will have some value of torque, and that value of torque keeps on increasing till it becomes 0 at some point when t is equal to alpha by beta. Now power here is a square term. This is parabolic, so you get a parabolic thing where the maximum power is here. So when you have the maximum power there, I would like my omega s. So when I'm using it as a generator, my AC motor or alternator or induction generator should have a frequency corresponding to omega s, corresponding to my 50 hertz component here. then this should correspond to 2 omega s. So that is why we used 2 omega s should correspond to this alpha by beta when the torque becomes 0. So that is how this gear ratio is calculated. So at this point, the shaft torque which becomes 0 is alpha by beta from this equation, but we want the value to be 2 omega s from the frequency of the alternator that finally should be given to the user load. So using that, we get this gear ratio 2 omega s equal to alpha by beta, and have your operating point somewhere close here where you can get the peak power. So a generic idle system consists of a turbine, a gearbox, a genset, and the sink. Sink will be load, any type of load. So this portion, the turbine with the gearbox, is the turbine portion. The generator, genset, can be a DC generator or a AC generator. Could be an induction generator or an alternator in the AC case. So synchronous or asynchronous, and then you can have the sink as a load, or you can pump back into the mains grid also. So these are the different applications which are there. Let us see a very common popular idle mechanism where an induction generator is used to interface the turbine with a sink. The sink could be the mains grid or even a standalone load. So typically what is done is, so you have an induction generator, it is a delta winding, there is this neutral and this is line. The wiring is done in this way. From each phase of it, it is brought out to this RCD. After the residual current device, you have an MCB, circuit breaker switch, and follow it up with capacitance like this, C to C, connected in the same fashion, and make sure it is C to C. This will form a open delta. You don't need 3 capacitances, you just use 2 capacitances. It is an open delta configuration. It will be able to give slightly less power than a complete full delta configuration, but it is much less expensive. And then I can draw out a single phase line across this capacitance C, and that goes to an IGC. IGC is nothing but an induction generator controller. It is basically something that will see to it that the load which is presented here is more or less constant. So what is done is, this will keep switching between ballast and the actual load. So there will be ballast and then there will be the actual user load. So this will see to it that if this load decreases, if the actual user load decreases, it will increase this ballast load so that the load presented here is always same. If there is no load, the full ballast load is applied here, and then the same amount of power is drawn. And when this is full load, this ballast load is cut off, and still the same load will be presented to this terminals. The reason that is done is the induction generator, the frequency swings widely with variation in the load. So therefore, it is always ensured that almost constant load is presented to the terminals here, so that the frequency of the induction generator doesn't change. So that is the function of the IGC, that is the induction generator controller. It basically tries to see that between this ballast load and the actual load, it is appropriately switched and presents almost constant load across the terminals of the generator system. So in this way, idle, a micro or a pico-idle system works, and this is a very simple configuration. The idea of a pumped hydro, where water pumping is one half of the part of the pumped hydro application where the PV is used for pumping water at any particular rate to a reservoir, and the other part of the application is from the reservoir the stored potential energy is converted and made available in an electrical form uh, compatible to particular loads. So this is the pumped hydro concept.